Okay, well, thank you very much for the invitation. I'm really happy to be able to have the opportunity to present the work. I must maybe warm. I come from physics, but all things relativity, gravitation, research-wise, are quite new to me. So I'm really happy to have the opportunity to participate in this program. I would be extremely happy to get feedback, to get comments, to learn about more open problems. Okay, so I just said before that I was very happy to present the results here. That I'm quite new to the mathematical physics of gravitation and general relativity. That's it, joint work, so with Matías and Paola, who's in Vienna, and that I would be really happy to get some feedback. So the starting point is Liouville's equation. So free transport according to, okay, there's a lot of things here. We have a function f that gives a distribution in the classical phase space. So x and p are position and momentum in R1, 2, or 3, let's say. F depends on the time and on position and momentum, and it gives this equation says that F is transported along the classical trajectories of a particle in a potential well, or in the potential given by V. So we have some abuse of notation where nabla sub x are the partial derivatives of f with respect to x1, x2 with x3, and so on with p and so on. Okay, so this is the equation. I guess in different contexts it can have different interpretations, but for this thing related to for us, it's mostly like a non-interacting limit of the Vlasov-Poisson system or the Boltzmann equation. So in this context, F, the density on the classical phase space is an empirical density, a macroscopic quantity related to some typical microscopic states where there are many identical particles, and we've computed the amount of particles in small boxes, and then we take some limits of infinitely many particles or something like that to get a continuous distribution. So that's the interpretation of this. So if you have Boltzmann equation, you usually so you usually put this part at the other side of the equation, and then you add a collision term. If you have the Vlasov-Poisson system, then this V would not be an external potential, but the potential generated by F through its space density. So this same F, but integrated over the velocities or p variables. Okay. Now, if you're lucky and this system turns out to be integrable, which means that you have as much conserved quantities as dimensions, then there exists a transformation to new conjugate variables that are called action and angle variables, where the actions are the conserved quantities. So here throughout the talk, they are K, K1, K2, K3, which will be, I don't know, energy, angular momentum, and things like that. And just to be fairly general, we assume that these K variables live in some set K in RD. Where K, if you think about the typical case that not typical, but easy case, where you have just D equal 1, and V is a potential that looks like this. So it goes to infinity at infinity, and it has a 0 at 0. Then you have a potential well, and then the set K will be the energy or some function of the energy, and it will take values from 0 to plus infinity. So that's one example to keep in mind. If you have potentials like this, K will take values. K might be the open interval from 0 to this value for the energy and so on. So since there are different possibilities and I don't want to distinguish all of them, we just call this set K. And then there are the other variables, they called angles, and so we will call them Q throughout the talk, and they are they live in the torus, so in the interval 0 to 2 pi, with the understanding that the function is periodic. If we arrive to 2 pi, we're back at 0. Should I say something else? So in these angle coordinates, if you compare to the previous equation, we got rid of one of the terms, basically. Here we had 2 gradients, and since the Hamiltonian only depends on the K variables and not on the Q variables, here the same equation takes a simpler form, and the coefficients here of the partial derivatives with respect to Q is a vector of the positive numbers, which are called omega because they correspond to the angular velocities. Once the equation is written like this, you can just you can solve it in the one-dimensional case. You can solve it always, and you can write f of t, q, and k as some initial condition, but instead of evaluating it in q, you evaluate it in q minus t omega, where omega was a vector, and k. Right. So once you've written this, you have the solution, and throughout we will call f0 the initial condition, which depends on action and angle, and f the distribution at time t. So unfortunately, this works on a quite restrictive and non-generic condition, except in one dimension, because you always conserve energy, but else it only happens in quite special cases, but many physical special cases. And one nice thing is that even there are systems that are not coming from this classical mechanics viewpoint on the first slide that are still admit this kind of action angle variables, like geodesic motion in the Kerr spacetime. So if you have many identical particles non-interacting around a Kerr black hole, then you also can write their distribution in this kind of form. So in this formulation of the equation, we will work, but keep in mind that this is related to some physical system by some canonical transformation. Okay, so far? Please interrupt me if it's not okay. So then mixing, it's really, I put some picture here of what happens to this equation if you have an omega that's not a trivial constant omega. So an harmonic oscillator would correspond to a trivial constant omega. Anything else will mean that particles which have different energies will go faster or slower. And so if I start initially with some kind of ball, all particles are like in one place in phase space, this ball will eventually stretch out into thin filaments. And so on point-wise, it's never going to converge. It is actually very, very oscillating. But if I take averages, then it will converge. And at first, it's taking averages. I thought it was like artificial, but actually it's, now I'm convinced of the complete contrary. If you're not, try to convince me back. Because F is this density, empirical macroscopical density associated to your distribution of many, but a finite number of particles. So F only makes sense if you look at its average values over boxes which will contain many particles. So depending on how many particles you have and how big is your space, these boxes are not allowed to be too small. That's basically it. And in this context, the idea of phase space mixing, so mixing in this microscopical phase space, is that you integrate the distribution f against some function of the action angle variables. It could be a function in the real physical space that we transformed to some probably more complicated function of the action angle variables. And we integrate it, and then we say that it's mixing if this thing converges to something time independent. And this time independent thing is actually easily obtained from the initial condition. So we will use a bar to denote for functions of action and angle variables. We will use a bar to denote the average over the angle variable. So F0 bar of Q and K is actually something that does not depend on Q, but I like to write it anyway, because then F0 and F0 bar depend are functions defined on the same space. Q here is completely irrelevant, because you take your initial F0 and you integrate over all the action variables, the D action variables that you have. So averages against test functions converge to a smeared out version of the initial condition. So you look at each value of K, you average, you look how many particles I have in total at this value of K, and then this you divide by 2 pi, so that you have something uniform in the Q variable. Okay, so this is the notion of mixing. I'm very vague about what is the test function. We could say that there is mixing if this holds for any real test function, so C infinity and compact support. And then we will see that actually the theorem allows us to take phi more regular. It's not really necessary that it's C infinity and compact support. Okay. So that's the idea of mixing. I think the word is very well chosen. If you look at the picture, maybe some references. So there are some older papers of Lyndon Bell, where he pointed out that this might be an important mechanism for homogenization in clusters of stars or galaxies. There's a more recent proof of Mouot and Villani about Landau damping. So that is in a plasma, where you also have laws of Poisson, but with electrostatic repulsion instead of Coulombic attraction. And they find that mathematically this phase-phase mixing that comes from the free transport equation allows them to prove this damping, so that oscillations are decreasing with time, even if there's no really mechanism to disperse them, like in a heat equation or something. Okay, so that's a bit of context about mixing. What we did is to take C1 functions. To avoid worrying about integration by parts and also about integrals are finite, we assume that one of them, for instance, the phi, has compact support, so it doesn't see the boundary of K, which might be there, and also the support is in a finite ball. And a frequency function of class C2, with the important condition is that it's Jacobian matrix. So omega was a vector of D entries, and then you make a matrix by taking the D partial derivatives of each of the D entries. So you get a square matrix. If this one is invertible for all values of the conserved quantities in our set K, then so we have what we had at the left-hand side in the previous slide. We have what we have had at the right-hand side in the previous slide. To be sure, I'll show you. So we put this one at, we subtract the limits here, and we put phi outside of the parentheses. And this, we don't take a limit, but we show that this is smaller than 1 over t, if we think about positive t. So that means it converges and it goes with rate 1 over t. This was not known in this generality. We learned a lot of a paper, fairly recent preprint by Jonathan Luck and one of his students, I think, where they do something similar, but they study a particular physical system in one dimension only, and they only study the Coulomb potential generated by the density. So we generalize the method, but many of the ideas were already there. And the method is a kind of vector field method. So vector field methods have been introduced to study wave equations, to obtain decay estimates, and so on. And typically the idea is, as far as I know, the idea of these kind of vector field methods is to look at conserved quantities. Now, this is the vector field, and you can check, just to check that W commutes with dt plus omega times the gradient in Q. So this is the operator of the free transport. So that means that this is a conserved, that this quantity is conserved. So from this you get conservation laws. If F is a solution, then also WF is a solution. And we know that if we are in action angle coordinates, the free transport preserves the measure of sets in phase space. So this gives us lots of conservation laws. So for F, but also for W applied to F. So WF it's integrated against any function of K. No, I don't want to call this function. Against any function of K is the same quantity, but at 0 Q K times G of K. And another thing about free transport, since we can say that we transport separately the positive part and the negative part of something, you can also sneak in absolute values. So F, by its physical meaning, is positive, but WF are derivatives, so they don't need to be anything positive. Okay, so this is the conservation law that will allow us to have the bound that's stated here with a C that is not depending on T. Okay, I think I forgot to say this. The C here is some constant, and it depends on everything except for T. So it depends on F0 and phi and on omega and on universal constants. And you can estimate it in terms of certain integrals of F, of its derivative, of phi and its derivative, and of the Jacobian of omega and its derivatives. Basically, it depends on all these things. So I'm going to quickly give the proof of the theorem for the case d equal 1, because it's a lot cleaner and it's not so much things to write. So we can keep in mind, maybe I'll try to put it somewhere here. So we'll keep in mind this conservation law, and okay, this is very small. I'm not sure if it's useful still, but anyway, we keep this in mind, and then we go bounding what we have on the left-hand side. Okay, So the first thing is that the first point is that the average at time of the initial condition is the same as the average after a time t. That's straightforward if you just write at f0 qk 0 bar was defined as. So here we're one dimension, so that's the integrals are just 0 to 2 pi f0 at some q prime k integrated in q prime, and then you can change variables and change q prime for q prime minus omega t, and you get the same quantity. So this is the same as the average. I'll just cheat. F of t q prime. So with this, what we had to bound was an integral from 0 to 2 pi, an integral in k of some function phi of q and k times f of t q and k minus this guy here, so 1 over 2 pi integral of f t q prime k t q prime. And then we have the q and the k values. Okay, so here, this integral, if I integrate just dq prime over 0 to 2 pi, that's 2 pi. So 2 pi divided by 2 pi is 1. So I can take this integral out in front of everyone. So I'll try to do this in this 2 pi and 1 over 2 pi here. And then I just have to do this. Okay. So this is what we have to bound. And then here we have a difference of the same function evaluated in two different values of q. So this f of class C1 and so on. So this I just write as the integral of its derivative in its second entry. Q prime to q, the integral of f of dq, but since I also call this variable q, I call this one q tilde or something. F of t q tilde k dq tilde. Okay, so we started from something simple and we made it quite complicated. And now, well, a first trick is in order to get bounds, we have to put absolute values at some moment. So I'll put them here to get something like that. And once I put absolute values, I first change the order of integration here to get out this integral of the interchange this integral with the k integral. And then okay, I'll just write out what this gives and then I will play around. Pi, 2 pi, and then I have an integral from q prime to q, tilde, and then I have an integral in k of all the same things I had before, right? Phi of q and k, and dq tilde f of t q tilde. Okay. Integrate in q tilde, in q prime, in q, and yeah, and in k first. That was the whole point of what I was writing. And then, okay, to have an upper bound, okay, that would be equality, but I want an upper bound, so I put the absolute values here. I put them here if I assume that q prime is bigger than q, and otherwise I have to exchange them to have absolute value, right? So in order not to worry about it, and also in order to get bounds, if I want to make it bigger, I'm integrating something positive, so I integrate from 0 to 2 pi. The interval q prime to q is always going to be smaller than the whole interval from 0 to 2 pi. And that's it. With this trick, one nice thing is that the q prime has disappeared, because it was only here, and now it's no longer there. So we can erase one of the integrals. And we have that this whole thing is actually equal to this integral gives 2 pi and it goes away with the 2 pi. So we are left with integral from 0 to 2 pi twice. And then the absolute value of the integral over k of phi, and then the derivative of f in its angle variables. So now there's something nice happening, because now is all the trick of vector field method in this context, at least, is to rewrite this derivative with respect to this this second variable in terms of this vector field W. So you can just we have a dq here, so you can just isolate it on one side, and you get that dq equals W minus dk, and then 1 over omega prime of k. And the great thing is there's a 1 over t in front of everyone. So this is our 1 over t that we needed to extract from somewhere. From here, I will, let's see. So what we wanted to bound was just some star, and we have it bounded by all of this. So I will make some space. Any questions up to now? Need 2 hands for this. Let's hope. Okay. So we have the absolute value of what we wanted was smaller than or equal to this. And then this here inside the integrand, I said that I wanted to write this 1 over t, which is a constant and can just get out of everything. 1 over omega prime, which for sake of saving space, I'll put it here. So here you see that omega prime can't be 0. That's you see immediately where the hypothesis is needed for the proof. And then this one becomes W minus T. Okay, fantastic. So it fits. So I have this expression, and then it's actually quite straightforward. So I have 2 terms. And I will use absolute values to write them, use the absolute value to write about as a sum of 2 terms. So we have our 1 over t in advance. I should have probably mentioned that we assume that t is positive. Otherwise, by taking it out of the absolute value, you get 1 over absolute value of t. So it's not a restriction. The q integrals we don't touch on for the moment. And then we get absolute value of the integral. I will open a big bracket here. Phi of q and k divided by omega prime of k of wf evaluated in t, q tilde, and k All of that's integrated in dk. And then we have a second term, which was the integral in k of phi of q and k divided by omega prime of k. And then we have the k derivative of f in t q tilde k. Absolute value, close bracket, and then we have to integrate over these q tilde and q. So this term, well, let's do one at a time. Maybe it's the best thing to do first is to integrate by parts here. There's an absolute value. I don't change signs, and we assume that phi had compact support, so we don't have boundary terms. So this becomes this. And then, okay, let's have a look at this guy here. What we do is we enter the absolute value, and then we exchange the order of integration once more. So I'll maybe put this slightly smaller to be able to write another line below. I don't know how big is the screen, how big you can see if you're there in Vienna, and also if you're behind your computer. I hope it's still okay. So what we do is, what we will end up with is the 1 over t, which we definitely want to keep because that was the whole point. And then we have a double integral from 0 to 2 pi, and the integral in k of phi divided by omega prime, and then w of f, I'll put absolute values everywhere, evaluated in t q tilde k. Okay. And what we do in this integral is you can do the q integral first. And in the q integral, the q dependence is only in the phi. So what you will actually get is the average of phi times 2 pi, because I don't have a factor of 2 pi. So we will get a 2 pi in front. We will erase one of these. It's kind of a big eraser. It's better. And put a bar over this one. So this one does not depend anymore on q variables. This one didn't have a q variable at all. And then we're actually in the form of this very, very tiny conservation law, which is here, because we have a function wf evaluated in t, q, and k against some function of k only. So here, for free, I can change the t for 0, and then I have just something that depends on the initial condition. And then in the second term, actually it's easier because the same thing holds if we don't put the w over here. So in the second term we do the same, and we have something that depends on the derivative of phi, and then we will get, if we integrate in q tilde, we will get the average actually of f, which we have already seen it to be time independent. So we will get the second term here. Should be also a double integral k of f0 bar k times dk phi integrating here I forgot to erase okay, this phi bar does not actually depend on q, so I can call it q tilde, and then we have here this one, and here this one. Oof, okay. So I hope you can still read a little bit. The bottom line is that we used the fundamental theorem of calculus to write this difference as a derivative. Then we used the vector field. We expressed the derivative in terms of the vector field, and this gained the factor 1/t. And then, yeah, we did some simple manipulations to check that we are really, it's really safe to put t equals 0 in all of these integrals. So we get expressions that only depend on the initial condition. Also here, if you do wf at 0, if you have t equals 0, then w is just decay. So we just have absolute value of decay of f in some variable. It happened to be called q tilde. Okay, so that's it for the one-dimensional case. The higher dimensional case is not really harder. It's just it's not as clean as here, but it's the way of gaining the 1/t is exactly the same. If you would have a transport equation in Euclidean space, then you could gain one factor of 1/t per dimension. But here, since we are on the torus, you don't actually expect that things are better in higher dimensions. The q variables live on the torus. So I hope I've convinced you that this is not something hard or sophisticated. And that has a good side because it's very flexible. One of the things you can do is, okay, many applications, it might happen that omega prime is equal to 0 at some point. What you can do is partition your the case space in two parts. A large part where, so okay, maybe first I say what's in the theorem. So if we assume in one dimension all the same, so we have C1 compact support, and then the condition of d omega invertible in one dimension, it's just that omega prime is different from 0. This holds except at one degenerate point or something, k1, but the second derivative is not 0 there. So, okay, if the frequencies would become constant at some interval or something like that, so omega prime 0 at some interval, yeah, then there would be no mixing in this interval. But if omega just goes to 0 at one point, barely, and second derivative is not different from 0, still nearby points will move with different velocities. So we still expect that mixing holds, and it does. But with our methods, we are not able to get a 1/t. We get a 1/t to the 1/3. So this is the theorem, and then the idea of the proof is to just smoothly cut f in two pieces. One piece that's supported an epsilon away from this degenerate point k1. So for this one, we can just apply the theorem, and we get a decay of 1/t. And then one part that is supported within, I don't know, 2 epsilon of this degenerate point. And for this, we can't apply the theorem, but we have something that's bounded in a very small interval. So these integrals can be bounded independent of t by 4 times epsilon or something, or the total mass times epsilon, something like that. Or the maximum of f0 times epsilon, something, constant times epsilon. Sorry. And then we have to, because in the constant of the previous theorem, we had a derivative of 1/omega prime, which is like omega second, which is okay, over omega prime squared, which goes to 0. So then you have some, it's not hard, but I'm not going to write out all the details here, but then you can choose the optimal relation between t and epsilon, and it turns out that it's that epsilon is like 1/t to the power 1/3. So that's one thing. And there's a second thing that I found very surprising, is that you can actually improve this argument, because okay, the whole point on the previous slides, 2 previous slides, was to make appear, I erased this derivative, but to make appear this derivative in Q tilde. And then we expressed it in terms of W, and then everything went smoothly. What you can do is use a version of Poincare's theorem. So we're on a bounded, we're on with periodic things. So we can, the integral of a function, we can bound it by the integral, some constant times the integral of its derivative. And then, so instead of dq of f, we have dq squared of f. And why stop there? You can iterate it again and again and again to get some power of dq of f here. And then if you replace it by this, you get 1 over t to some power. And then you have to manipulate this whole big product in a form that you can still integrate by parts and show that it's time independent, but you can do that. So then you get this kind of statement. So we need more regularity. We need to take L derivatives. And since omega prime appears, we need L plus 1 derivatives of omega prime, still compact support. Especially in this case, we don't want any boundary terms because we have to integrate by parts a lot. And then these absolute values are in a strange place, but okay. So the same quantity is bounded by some constant depending on L. So you pay something. This constant will get bigger and bigger by t to the power L. So in particular, if everything in your system is C infinity, then you have more than polynomial convergence to this this equilibrium value. Okay, so these were a few things that we could do. And then a final thing that we wanted to look at in the paper is because of this motivation coming from Vlassov-Poisson, the Coulomb potential generated by this density has a special role. And okay, we define the Coulomb potential as a solution to Poisson's equation. With okay, if d is larger than 2, then you have decay. Typical boundary conditions are to ask that it goes to 0 at infinity. In one dimension, you can ask for 0 at minus infinity, or at plus infinity, or at 0, or at any point of your choice. So take this one. And then, okay, but this is in the physical space. The action angle variables, they live in a different space. So we need a transformation, and we need that we can take the derivatives of this transformation. So that's just what's in this box. Sorry for this slide, it's kind of full. And then we take a distribution that's not seeing any boundary. So G is the set where in the physical phase space where you get to where the bounded trajectories that we are interested in live. And if we assume additionally that that we have a uniform bound on F0 and in its gradient, because now phi is not having any compact support, right? So if we just ask enough things here, then we can still make it work. And the way that we make it work is by writing this Coulomb potential as a convolution with in 3 dimensions 1 over x minus y. So 1 over x minus y will get converted to action angle variables, and this is really not fun to do. But if you assume that transformation to action angle variables has certain regularity, you don't actually care for what it looks like in the end. You just use the chain rule, and you just the regularity that 1 over x minus y has gets transported to this 1 over x minus y in action angle variables. and then you apply the same theorem. So the phi you have is certainly not satisfying the hypothesis of the first theorem, but you can make it work by asking a little bit more of the F0. And now that I'm looking at it, I have the impression that we're actually asking less of this F0, but that's because of the first theorem we asked more than we need. Okay, so if we ask some things of the F0, then it can compensate the singularity of 1 over x minus y. And that allows you to have the same kind of bounds. Okay, so this covers the results I wanted to present. There are many open problems, and I would be really, really happy if you have more ideas, more questions. So one thing that's like, okay, we just have to sit down and calculate it, is to generalize this result over when you don't have invertibility. In the one-dimensional case, we saw that it worked easily. In higher dimensional case, this is relevant for the Kerr black hole, because there is a curve in the two, if you take Kerr and you take the gas constraint to the equatorial plane, then there is a curve where this determinant finishes. So this is work by Olivier Serbach and Paola. And so it would be nice to see if in that case as well we could still have mixing with at a slower, probably at a slower rate. Then of course I think the main question is how to use this, how to use it for nonlinear stability, or for more physical cases where you do have interactions. There's this very exciting thing that if you have equilibrium states of Lasso of Poisson and then you perturb them, you find these oscillating modes. So two leading order things do not converge to some equilibrium. So this is maybe in some systems there's a kind of competition between this mixing and this oscillatory behavior. And also what I think is, luckily many physical systems are integrable, but generically they are not so in 3 dimensions. So what can we do? Can you say something? It's not that the theorem does not apply, it's that the statement makes no sense, because in the statement we average over these action angle variables. What happens else, I don't know exactly what we could hope for and how we could formulate it. So this is all. I just put a very minimal biography. So the paper of Chaturvedi and Luke that I mentioned. So vector field methods have a long service, a long theory, so a long history, also in different kind of equations. So there's a paper by David and co-authors. They are usually assigned to Kleinerman for the wave equation. Lyndon Bell, who mentioned the relevance of mixing for physical reasons. The paper by Clément Moreau and Cyril Villani on Landau damping. The works of Paola and Olivier on phase-space mixing in Kerr, and also in this paper, external gravitational potentials. They actually check this condition that omega prime should be different from 0. They check it for many potentials that have a certain relevance in astrophysics. So this also gives a class of concrete examples where this theorem applies. And also, this one is a vector field method and Lasso of Poisson, so it's related, but it's not really, it's not the same vector fields. It's that's just, but I wanted to mention it because it's still quite related. Okay, thank you very much. I hope that we can make questions work. I'll be happy to try to answer them.